Okay, so let's wrap up our first lecture on FETs with a couple other types of FETs. And before we go into these, we need to review some basic concepts. Particularly the type of FET we're going to talk about next uses a Schottky or metal semiconductor contact to make the gate contact. So the particular case we're going to look at is rectifying or Schottky contact on N-type material, as you can see here. And if you recall, when we set this Schottky contact up to basically get a reverse bias on this, we would want to put negative voltage on this side, which raises the bands up and then further increases the depletion region this way. And the key thing we said that even though I raise the bands up and I get a steeper slope, I don't get much current because I'm limited to reverse saturation current of holes moving here. And even though I could shift this up, there aren't that many holes here. So the cliff size is not what matters, rather the thermal generation of holes, and that's why I'd be left with just I naught. And I naught's really small, so this is probably not a bad gate to use also if I want to use a gate where I use depletion region to modulate a channel. So let's look at So what I want to do then is modulate the reversed bias depletion region for a Schottky contact and use that as my gate. And again, here I am with positive voltage. I don't want to do it that way because with positive voltage I start to get a ton of current spilling over from the N-type side into the metal, which has positive voltage. What we're going to do is instead put negative voltage on the metal, which is going to increase our depletion region width. And so here's how I make this device, and I'm going to call it a MESFET. MESFET stands for Metal Semiconductor Field Effect Transistor. So the ME stands for metal and the S is for semiconductor, meaning that I'm just using a Schottky type contact. It's not a JFET, it's a metal semiconductor field effect transistor. So if I look at this device here, what I'm going to do under the gate is I'm going to modulate the conductivity or the electron flow through this channel through this depletion region here under the Schottky contact there. If you look at what I have here, I've epitaxially grown, meaning it's not a wafer I start with. I grew a crystal layer of N-type gallium arsenide on top of a semi-insulating gallium arsenide substrate. The reason why I use a semi-insulating gallium arsenide substrate is because it has no doping level and it's pretty much as it says. It's fairly highly insulating. So therefore, all I have to do is modulate the current flow through the conductive portion, which is this grown layer of N-type gallium arsenide right here. And so what I need to do then further, if I make devices, is I grow this layer, but then I etch the sides away, so that if I have a device here, it won't cause current interference with the device over here or a device over here. They'll basically be isolated where I etched it out. So this basically allows me to have current flow just through this device. I can wire to the next device over here, but I'll have air in between, and the substrate doesn't matter because it's insulating as well. Now, the key thing that's attractive about a MESFET is two things. One, all I have to do to make this junction here, unlike a JFET, is just pattern a metal. And I can make that really small. It's very easy to make a small metal pattern. We'll talk about why that's important in a second. The other reason why I like this is I'm using gallium arsenide instead of silicon, MOSFETs or JFETs, and there's three reasons why I like that. I like gallium arsenide because compared to silicon, which has a band gap of 1.12, gallium arsenide has a band gap of 1.43, meaning it can take higher temperature. I can run higher current through this. Remember, a wider band gap means that it takes more temperature to thermally generate carriers. And so I can get this thing hotter before the thermally generated carriers start to cause this thing not to behave appropriately. That's what I get with a wider band gap. The other thing nice about gallium arsenide is the electron mobility. Compared to silicon, gallium arsenide has a much higher electron mobility. Electron mobility gives me higher current, since my current is flowing from here to here by drift, right? It's just voltage through a semiconductor. So high mobility helps me there. And again, as I noted before, it's an advantage to have a small gate metal here. Let's go through all these in a little bit more detail, but again, my drain current versus drain voltage would be as follows. If I increase reverse bias on this system, putting more negative voltage on the gate, then I will turn the current for this off, and I still have pinch off and saturation just like I did before, just like for the JFET. So again, why do I get higher speed? Well, again, higher mobility for gallium arsenide gives me greater drift current for a given E field, for a given voltage applied from the source to drain. Again, the wider band gap gives me higher temperature operation, which means I can do more current, which is helpful, meaning that I can also run a chip hotter. If you look at modern computing chips, one of the challenges you have is that they can't run them any faster because they get too hot, and they're using silicon. And so chips that if you make them out of wider bandgap materials, you can run them even faster, have more power dissipation from all that charging and discharging, and therefore get higher speed operation. Now the final thing, and this is the one I want to spend the most time on this slide on, is the simple fabrication of just patterning the metal allows me to get a smaller channel length here. Well, how's this help us? Well, think about connecting the source of one JFET to the gate of another JFET, and why would a smaller gate help us? Well, there's two ways it helps us, and this is really important, okay? First off, the gate we have here has a capacitance, right? And so this gate basically acts as a capacitor, right? So I've got a capacitor at my gate, okay? So there's my gate. And if I reduce the width of this, I reduce the capacitance because my area of my capacitor went down. That's important because that's half of RC time constant for a circuit. If I reduce the capacitance by a smaller gate width, I've reduced my capacitance. However, I get another advantage out of this because I also have resistance decreasing as well. So if I make this more narrow, then my length of my channel has decreased and my resistance of the channel decreases as well. So down in that channel, I've got a resistor, and so if I make this narrower, I don't have to go as far, and my resistor will go down as well, and my RC time constant goes down as well. So here, let me give you a diagram of a little bit what this looks like and why this matters in a circuit. I'll do the best job I can here. Okay, so let's say I have a bunch of devices here, and don't worry about the voltages or things like that. But let's say I'm going to do an input at this gate here, so I'll bias this one, and that'll be my input voltage. And then I'll use this transistor to modulate through the drain to the next transistor. And then this transistor will modulate through the channel, through the drain, to the next transistor. Well, again, if I look at this, let's see if I can draw this here and do a good job of it. Again, here I have a capacitance, here I have a resistance, here I have a capacitance, here I have a resistance, here's another capacitance, here's another resistance, if I were to keep this going. And so the beauty of basically reducing gate width for any type of field effect transistor is that if you look at RC time constant, it goes down in both R and both C. For example, C decreased because the gate width was less here. R decreased, so my resistor going on to my next capacitor, charging time for this one, decreased because both resistance and both capacitance decreased. Same things here. Made this more narrow. This resistance decreases, going to a smaller capacitor here. And so my overall RC time constant goes down. So, a simple calculation. Let's say that I basically took my gate, let's say I'll call this my gate length here is L. Let's say I take L from 4 microns to, let's take it down to 2 microns. How much would my RC time constant go down for each device in a circuit like this? Well, it's simple. Both R and C get cut in half because I basically reduced L by a factor of 2, right? Therefore, if both R and C go down by a factor of 2, RC goes down by a factor of 4. And so you can see every time you decrease gate width for a transistor, MOSFET, MESFET, whatever type of transistor it is, you get a big bang for your buck in terms of reducing the RC time constant and how fast you could then switch these devices in some kind of a circuit. Okay, so let's move on to another type of field effect transistor, and it's going to take us back to heterojunctions. So again, a homojunction was when we had silicon and silicon, or gallium arsenide and gallium arsenide, same material systems, right? And so when you join those together, you get a nice continuous curvature and continuity for the bands when they come together. Now, for this device, we're going to next look at something called a high electron mobility transistor, which is based on a heterojunction. And if you look at all the highest performance devices, LEDs, lasers, BJTs, and even this device called a HEMT, they all use heterojunctions. And so for this device, the heterojunction is going to be based on aluminum gallium arsenide and gallium arsenide. And these materials have different electron affinities and different work functions. And so when I join these together, what's the first thing that you know must happen? Well, always you know that the Fermi level has to line up, so we'll line these up. Let's take a look at this on the next slide. So, I'm going to take these two heterojunctions, I'm going to join the semiconductors, and again I'll review how we do this. The Fermi levels have to always align. So I have these two materials, the Fermi levels have to align. So that means this side has to go down, this side has to go up. The other thing I know I have to do is I have to maintain the delta EC and the delta EV at the junction. So if it's this much higher than this, then I have to maintain that. So look, this went down, right? This went up. But right here at the interface, I made sure that this was the same amount higher down here. Same delta EC, same one in terms of which one's higher and lower compared to the original alignment of them. I do the same thing for EV. This one has to be lower. It's lower on this side, same delta EV. The next thing I need to do, after I've taken the deltas into consideration and I've already shifted the bands so the Fermi levels line up, is that I need to connect everything. And so I know I've got some band bending because I get depletion as these things shift. And when I do that, I'll basically connect these points to the rest of the conduction in the valence band. So I know that these had shifted up to here. Here's my connecting point here, and I'll draw a smooth line in between. I'll do the same on this side. And when I did that, the last thing I did was I took in doping effects. And so if I looked at the fact that this is N plus and this is just lightly doped N, then most of the band bending will be on the lightly doped side, so I have less band bending and less depletion width on the heavily doped side. So, what is this bias basically in terms of transistor operation? Well, remember, electrons are like water. They're always going to find their way to the lowest points of the conduction band, right? Look at this little feature right here, this little dip in the conduction band. If I design this right, this basically forms a quantum well. In fact, if you remember from quantum mechanics, you probably did a square potential well, and you might have also done a triangular well. This is a triangular quantum well. And when I do that in a quantum well, you know that instead of having a continuum of states like you have in the conduction and valence band, where you have, just a nice density of electrons everywhere, in a quantum well, as the quantum well gets smaller, the energy levels break up into very uniform and discrete energy levels. And so I'll have a bunch of electrons at this energy level in the quantum well and a bunch at this energy level and none in between. What this does is it creates what we call a 2D electron gas, meaning that this is a sheet, like a two-dimensional sheet, right? It's an electron gas. They call it a gas because the electrons are freely flowing around like a gas. And what happens when the electrons are put in this very orderly fashion is the mobility shoots through the roof. In fact, the mobility reaches levels of tens of thousands to hundreds of thousands. The reason why that is unlike a situation where out here I have electrons everywhere, when you try to put current flow, the electrons are running into each other because there's always an electron right next to them. Well, in this case, I'm putting the electrons in a very nice orderly sheet here so that when the electrons flow, they don't bump into each other. Now in this device, the way it's going to flow, let's see if I can draw this. It's not too easy, but let me see if I can do it. The electrons are going to flow, there we go, I did a pretty good job there. So there's my view of this thing. There's my energy levels, okay? The electrons are flowing along this channel, so they're flowing into the plane here. And so now I've basically put them in this nice, orderly channel that they can flow along. They don't bump into each other, and if they don't bump into each other, then my mobility goes through the roof. That's why we call this a high electron mobility transistor, or a HEMT. I get extremely fast speeds because I get a higher current density, reducing R in my RC time constant equation. Let's look at how we modulate this. So here's that same device where I've got N plus aluminum gallium arsenide. Here's my lightly doped gallium arsenide underneath it. Okay. Here's the aluminum gallium arsenide. Here's the lightly doped gallium arsenide underneath it. And then I just basically put a source contact, a drain contact, and a metal Schottky contact. Okay. Now looking at this, here's my 2D electron gas here. It'll be all the way across here. This layer is really thin, so it's really easy to get current from the source and the drains down to the 2D electron gas layer. Once it gets in there, the mobility is extremely high, such that I get a huge amount of conductivity here. So getting current through the super thin layer here, and along this very high electron mobility, high electron gas, and out here, there's almost no resistance. And so my R of my RC time constant for a circuit made of these things is very low, because I've got my 2D electron gas. Again, my flow of electrons, as I showed you on the previous slide, it's in this direction based on how I bias it here, which is into the plane here. So I'm looking down the channel here, and here's along the channel. Okay? Now, how do we turn the device off then? Well, what we do is we put a negative voltage here on the gate. Negative voltage raises the bands up, and if we raise the bands up, as this goes up, I lose my potential well here, and I lose my 2D electron gas. Even though this is heavily doped aluminum gallium arsenide, and this is lightly doped, losing that mobility of tens of thousands to hundreds of thousands basically reduces the current so much that we can consider this device to be turned off. Now note, what you may need though is you may want a Schottky contact here that will deplete the N plus aluminum gallium arsenide. If you do that, then you're going to even get better performance because your off current will be even lower. And so if I did this right, I'd put a Schottky here that would deplete this as well when I start to turn this off, so there's no leakage current through here either. And again, this is lightly doped, so this is basically resisting, as is this. So let's go back to the picture for the day, which was a high electron mobility transistor, and let's see if it starts to make sense. So let's look at this device. Here's the source, here's the gate, here's the drain. And my first question is this device on or off? Well, if you look at this, here's my plot of electron concentration. I can see that I have a very high electron concentration, orange, right here. So here is my 2D electron gas. Okay? This is all heavily doped, so I easily get my current down to here, and then it flows from drain to source or from source to drain. Okay? And this is N-type material, of course, since it's electrons. Now let's look at the second question I have here. Look at the depletion region here. Why is this triangular in shape? Well, that tells me that first off, I am using a Schottky contact to deplete, because look at my concentrations. They go down way below 10 to the 10th. This is, orders and orders of magnitude lower concentration, so it depletes out here. But furthermore, whenever you see this triangular shape, you know you've got a voltage applied. And so that's telling me that I'm getting extra reverse bias based on the gate to source voltage, giving me extra reverse bias. and that the gain to drape voltage is somehow reducing the reverse bias in the depletion. So I'm getting basically that same sort of pinch-off type effect you saw for a JFET, where the channel has this sort of shape to it. Here's a paper from a press release from a company a little while ago that had gallium nitride HEMTs. They said that they had some extremely high performance, actually a world record for transconductance. Look at their transconductance they report for this gallium nitride HEMT. 350 millisiemens per millimeter. Remember we said that the real figure of merit for a transistor like this is GM over the width of the device, Z, so you can't cheat and make it super wide to get more conductivity. Well, that's why they're saying per millimeter. So then you can qualify this, because if you made the device wider and wider, of course you could get more current, more amps per volt, but that doesn't matter because then you're paying more cost of the size of the device on the wafer. So this is the true figure of merit. Maximum frequency 115 gigahertz. Very fast device. To make it fast, look what they've done here. This is the gate. This is the gate, and there's the gate contact there. What have they done here? You can see that they're going through huge efforts to make the gate as small as possible. So again, they can reduce the gate capacitance and reduce the channel resistance such that in a circuit like this, they get a small RC time constant. So it's all about making the transistor smaller if you want faster switching speed. In fact, I think they say here, a metal gate footprint of approximately 50 nanometers is what they have there. Here's another example of a commercial HEMT. This is a gallium nitride HEMT produced by Cree. Cree is mainly known for making gallium nitride LEDs, but they use their same gallium nitride semiconductor technology to make transistors as well. This one here, it's basically an RF power HEMT that goes up to pretty high power, 6 watts in a very small package. Gallium nitride is a wide bandgap material, so that's particularly why they choose that, in that this thing can really take the heat. You can make a nice small package, drive it hard, and you don't have to worry about the heat dissipation as much. If you look at one of the most interesting things for this one is the pricing for this. So this product here, this is 2011, it's probably dropped a little bit since then, but this exact product here is $48 from DigiKey, okay? And this is the, I think, what is this, the 6 watt version? If you want the 220 watt version, yep, I said 220 watts, you can get it for $900 at DigiKey. And so the reason why I like to show this slide is to remind you that if you want to work in semiconductors and you've worked in the advanced devices like a HEMT with an advanced semiconductor like gallium nitride, work for a place like Cree, you could probably make pretty good money because they're able to charge a good amount of money for the devices they create. So there's still a lot of interesting work going on in semiconductors, and those that are creating new devices are getting paid well for the capability they create. Last slide I have here is to basically revisit the diagrams of different transistors. So we talked about BJTs and why they're pinched in and why you have the arrows here for the emitters like this for NPN versus PNP. Look at JFETs here. There's a difference between a MOSFET and a JFET, and the biggest difference is the arrow. Why do I have that arrow there at the gate? Well, the arrow at the gate tells you the current direction, okay? So if this is an N-channel field effect transistor, let's draw it real quick. I've got my N-type material, and then I've got my P-type material, okay? Let's look at the current for this. I'm going to reverse bias this, okay? But in terms of putting positive voltage, if I'm looking at the gate, I'm looking at it in terms of being a diode, right? And so there's my diode there, if I were to draw a diode. And so if I were to get a lot of current flow and bias this the wrong way, the current flow would be into the device from the P to the N. And so that's why when I have an N-channel JFET, they draw the arrow there, meaning the diode is in this direction like I would have for an N-channel JFET. For a P-channel JFET, the diode would be in the opposite direction, hence the direction of the current shown in the opposite direction. So it's not the current, it's not the reverse saturation current, rather it's indicating the direction of the diode current, which you typically want to avoid. Okay, at this point, you're ready to wrap up and finish. So, first question. Why do people create and use MESFETs? There are 3 advantages we highlighted. You should know those. What kind of equations are needed to predict JFET and MESFET performance? This is a pretty simple question. This whole course has been predominantly built on one type of 2-terminal semiconductor device and its equations. And we're just using those equations over and over again to start predicting more complicated devices like BJTs and now JFETs and MESFETs as well. Next question, why do people create and use HEMTs? There is one big reason why you create a HEMT like this. Last question. How much bigger is the channel mobility for a gallium arsenide HEMT versus a gallium arsenide MESFET versus a silicon JFET? Just go to the previous slides and write down the mobility for each, and you can see how each technology becomes more powerful in terms of the channel conductance, therefore the maximum current flow, and also therefore the RC time constant as you try to modulate these things very quickly. And that's it. See you in class.